Dear students, let us continue our video lectures on advanced digital signal processing. Let me share the screen. In the previous video lecture, we have introduced and discussed about discrete Fourier series. We have seen how the frequency domain representation for discrete periodic signals can be taken. And we have also seen with few examples how to compute the discrete Fourier series. We have posed a couple of problems on how does it relate to discrete Fourier transform, discrete time Fourier transform, and also on the looking at discrete Fourier series quotients as sampled versions of the discrete time Fourier transform. Now let us continue our discussion on properties of this discrete Fourier series. See, when we wish to study the properties of discrete Fourier series, what is of importance is to understand what does happen in time domain and in frequency domain. How does it reflect in frequency domain when I perform some operation in time domain, right? So let us consider an operation like shifting of the sequence in time domain. We will subsequently consider different operations like multiplying the time domain sequence with complex exponential signal and so on. Okay, performing convolution of two signals in time domain. How does it reflect in frequency domain and so on, right? So the discussion whole now is on the discrete periodic signals. Okay, so let us assume that we have a shifted signal of this discrete periodic signal. See, what do we mean by shifted signal? Say, assume that x1 tilde of n is related to x tilde of n as x tilde of n plus 2. Okay, so now this is a advanced version, right, of the x tilde of n by 2 units. See, when I advance it by 2 units, what will it happen? Instead of occurring this value at t equal to 2, it will occur at t equal to 0. That's what you can see here, right? And I can sketch the signal, the whole signal, the periodic signal, shifted by 2 units. However, see, if we see any one period of this periodic signal, it will be clear what will happen and what's happening in the other, the whole periodic signal in other periods, right? So it's of common interest and the procedure to look at only one period, okay, and understand what does the implication of this property, whatever is the operation that we are doing in time domain. So let us understand only for this period ranging from 0 to 9. So that is n equal to 10 samples, which is the which encompasses one period of this discrete periodic signal, right? And in this 0 to 9 samples, so if I am able to understand what the implication of this, I will just repeat this again and again to know the whole periodic signal or to visualize the whole periodic signal. Fine. So let us see from 0 to 9. So what will happen, as just we discussed, what the value at t equal to 2 now will sit at t equal to 0, okay, and so on. That means it will happen 2 time steps ahead of the earlier. Okay, that's what is done in this. So this is, so if you see this, what is happening here is like a like circular shifting operation rather than a shift like the a time shift operation. You can visualize this better by relating this to a circular shift operation. That means, say if I have n samples. Okay, so right, n equal to 0 here, fine, and n equal to 1 here, and so on till n equal to, so it keep moving, it keep okay, so this is n equal to n minus 1 is here, right? So n, if I look, if I sketch the samples on this circular diagram, so that is, this is x of 0 will be here. Okay, for the original signal x of n, if I sketch it here, x of 0 is here, okay, x of 1 is here, okay, and x of n minus 1 is here, right? And the shift by 2 units is, or the advance by 2 units means that instead of starting from 1, okay, now I may start from, right, x of 2, right? So instead of starting from here, okay, I may be starting from here and ending where? Ending at here, right? So that's how you can visualize this. Okay, the magnitudes are on the are the projections here, right? So it's like this. Okay, so you can see that these sample, if you consider only a particular period, the shift whatever we are doing here is like a circular shift rather than a linear shift, right? However, if you see the whole, if you notice the whole signal, the shift we are doing is linear shift itself, and the periodic signal itself is being shifted by 2 units this side, right? To make the advancement. Okay, to occur the sample little ahead in time, right? Okay, so and this kind of circular shifting, okay, can be visualized better. Okay, so visualize better through this uh, mm, through this kind of expression. So where you can see that either delay or advance, whatever, by n naught units is equal to n minus n naught modulo n. This modulo n operation enables us to always confine this to one period. Okay, 0 to 9 here, right? So if we now say if we shift here, this one will become say minus 1, then this modulo operation will make it n minus 1. That means instead of here, it will be at n minus 1 position. Instead of here, okay, so it will be n minus 1 position, correct? So that's what has happened here. You can see this. This is at n minus 1 position instead of at 1 position. Okay, similarly, if you shift by this by 2 units, then what will happen? So you can see that this will be shifted by 2 units, and these samples will come and sit this side, right? So then the shift will be from, say, instead of moving, advancing is this side. Okay, we are starting from here. If you advance by 2 units, if I delay by 1 unit, I might have started from here, and then the sequence will be like this up to here, right? Hope you got the point, right? So if I delay by 2 units, then I would have started from x of n minus 2. Okay, if I would have started from here rather than here, right? So this is delay by 2 units, and this is advance by 2 units and delay by 2 units. Okay, so for advance, we will start and end here. For delay, we will start and end here, right? Like that it goes. And the magnitude of the samples, here you can see n equal to 0 is this sample, n equal to 1 is this sample, and so on, right? And this mathematically we relate by this modulo operation. So any shifting for the periodic signal, we can easily account within this period by this. Hope this is understood. Now, if this happens in the time domain, what's the implication in the frequency domain? Okay, so let us see that now. So assume that there is a delay by n units. N naught may be n naught units. N naught may be positive or negative. In the previous case, you can consider that n naught equal to minus 2. Okay, so n naught equal to minus 2 here, right? And now, if you apply DF, if you want to find what is the effect in frequency domain, what do? We take help from first principles, and hence we put it here. There is a modulo n operation here if we want to strictly restrict to this 0 to n minus 1. Okay. And there's an expression. This is by definition of discrete Fourier series, right? And now we can substitute for n minus n not equal to n dash, and we can compute this with little bit of simplification, and it can be seen that this is roughly computed over one period, right? And this summation is again over one period, and these are corresponding exponentials, right? So all the time, so this n dash covers over a period of time. Okay, irrespective of, see, for example, if this is a periodic signal, okay, if we start from here to here or here to here, we may complete all these samples. However, the corresponding exponentials will also be correspondingly given here, right? And okay, so now this is the term which is, so this term is equal to x tilde of n, x tilde of k, and this is the additional term that comes because of the n naught term here, okay, because of the n naught in the in this expression. Because of n naught, you get this term, right? So this can be simple. This can be written in a simplified notation with wn n naught into k. Okay, where wn into n naught k will use a shorthand notation. Oh, sorry. Will use a shorthand notation for this. Right, n indicates the period, n naught and k are the time and frequency variables. This is a fixed time variable and this is a varying time frequency variable because we are representing this in frequency domain. Okay. So let's move on to the discussion on the other property. So now if we, this is shifting property. This we can refer to as shifting property in time. The other property of importance is multiplication with complex exponential in time domain. Okay, so the effect of multiplication with complex exponential. Okay, yeah. So this you can see that we are multiplying with a complex exponential signal here, and this in turn reflects as, so this can be simply absorbed in exponential term, and this if we want to write in a simplified version, this is the frequency quotient of x tilde of like computed at k minus k naught. Okay, so that's what we have written here. And modulo n will come if we want to represent only taking one period of the frequency domain information to represent the whole no, frequency spectrum, right? So this k minus k naught may fall beyond 0 to 9, and this modulo n will enable us to write this the frequency quotients in if even if we have the frequency quotients of 0 to 9 in our hand of x tilde of k initially with us, right? So even if we have one period of x tilde of k, that can be used to write x tilde of k minus k naught. Now then let us discuss on the next property that is somewhat special to discrete Fourier series and discrete Fourier transform. Even though in other Fourier transforms, we have seen that if we, based on some basic relationships of the time domain and frequency domain, it is easy to either apply the frequency domain to time domain or time domain to frequency domain transformations at different times. In this DFS and DFT, we have a specific expression guiding these frequency and time domain relationships. One main reason being, you can see that the nature of the frequency domain quotients and time domain samples are similar here. time domain sample is also periodic with period n. Frequency quotients are also periodic with period n. Okay. Similarly, this is also discrete and frequency quotients are also discrete. This enables us to write a simple and direct relationship between the time domain and the frequency domain operations. So if you want to do vice versa, that means sometimes see computing frequency domain to time domain transformation may be easy. Sometimes time domain to frequency may be easy. Okay, but however, the problem may be given in time domain with a complex function like this, and we are asked to find the quotients. See, in this case, for example, x tilde of n, if it is defined like this, it indicates that, so we have a sinc function in time domain, right? We know that the Fourier transform of a Fourier transform, discrete Fourier series representation of a rectangular sequence in time domain is equal to sinc in frequency domain. That relationship we know before. Using that, can we simplify the computation of frequency quotients for the sinc in time domain? That's the question now, right? So let us assume that given this information, like given this problem of finding discrete Fourier series quotients of x tilde of k. Okay, we see that the duality property that we derive now will help us to target this easily. Okay, so let us first derive this duality property. So what does this tell is, say if I have the synthesis analysis equation like this, okay, can I now use this analysis equation, okay, and synthesis equation as well, and relate the uh, time domain samples and frequency domain quotients effectively through a simple expression. Okay, so let us start discussion on the analysis DFS equation. It is like this. Now, if we have similar expression as this in frequency domain, okay, can I leverage it in time domain and get the frequency domain representation? That's what is the question. So let us change of variables. That means we want to switch from time domain to frequency domain and frequency domain to time domain with the help of this duality, right? So thus what we do is, let us interchange the variables n and k. So when we interchange the variables n, this becomes n and k is here, right? You can see this. However, now if you want to write this in a simplified notation, what we need is a positive sign here. Also, we need a term 1 by n here. Okay, how do we get that? We can write in slightly by rewriting. So we can slightly rewrite this x tilde of k e power j 2 pi by n into minus k, right? So this okay. So and let us multiply and divide by n to get the 1 by n term. So given this, what is this we can write? We can simply write this as x tilde of minus k. This is nothing but the synthesis expression for discrete Fourier series, right? So this is the analysis expression, and by change of variables and small algebraic operations, we're able to get the synthesis expression here. So we can write in frequency x tilde of minus k, right? The samples now becomes the quotients. Okay, so we have written like that, and quotients becomes the samples. Okay, with a small change of variables and so on, right? So, and this relation now will enable us, okay, to easily switch from time to frequency domain and frequency domain relationships to time domain relationships. Okay, so now you can see that x tilde of n is equal to so if you take DFS for x tilde of n, then you get n times x tilde of minus k. Okay, So let us see how to make use of fit or how it can be useful. So assume that we have here x tilde of n is a discrete sink. The question is to find x tilde of k, right? What we know is x tilde of n, that is the rectangular sequence if you have it in time domain, the DFS is S discrete sink. Fine, this you can see here. This in frequency domain. However, what we need is, if we have this in frequency domain, this in time domain, okay, that is discrete sink, okay, in time domain, what is x tilde of k? Will this be exactly equal to this? We will not be able to say like that in general. This shape will be similar. But what this duality property says is not just the shape, but it gives the magnitude scaling or the scaling and also any transformations involved, right? Any transformations means here what is involved? Minus k. That means a, so this exactly will be, DFS will be exactly similar to the time domain expression. Okay, time domain thing. However, the DFS quotients now are exactly this, only with small change of scaling by n times. That's what is incorporated here, and a flip around 0, right? If you make a flip around 0 for this, what will happen? All these things will go in this side, right? And hence, you can see here, flip around 0, minus k, right? I think flip around 0. So let us sketch this again. So you have at 0, whatever you have is n. Okay, magnitude is n. At whatever you have at 1, now will appear at minus 1, right? And minus 2, minus 3, and minus 4. Plus 4 will become minus 4, right? And then minus 5, minus 6, minus 7, minus 8, minus 9, right? However, in this positive direction, what will happen? What you had before here, okay, in negative direction, sorry, okay, these values, minus 1, minus 2, and so on, these will come here. So there will be 0, 0, and so on. So if you see the signal now, from minus 9 to 9, if you see the signal, sorry, minus 9 to 0, if you see the signal, or minus 10 to 0. Let us see, since we want to take over same one period, okay, right. So, and at 10, what shall happen? It will again be 1, sorry, n. Okay, this is the signal you can see. So in one period, if you look at the we can directly write x tilde of k, it's frequency domain quotients, okay, that they look like this. Fine. So now if you see from 0, it will be again 5 zeros and then repeatedly 4 ones. Okay, but if you see the whole signal, it will be like this. However, please note that there is an additional term here that we have not considered in the above discussions. Okay, so when we compute DFS, there will be e power. So let us write that as well. X tilde of k, x tilde of k is equal to e power minus j 2 pi by n into k into n naught by 2. Okay, so this is the term here. So because of that, you will have this x tilde of k, right? So this term is not here. So that term, say, assume that this also has that. Okay, e power minus j 2 pi by n into n by 2. Okay, n by 2 into k naught. Okay, so so that comes as a phase term for this. right? Okay. So this essentially guides the transformation from complex time domain expressions to frequency domain transformation, or complex frequency domain expression to inverse DFS computations. Okay, this is the advantage of this property. Fine, let's move on to the discussion on next set of important properties. See, if we perform multiplication in time domain, how does it reflect in uh, after discrete Fourier series? Okay, if you take in frequency domain. Okay, because see, if you multiply also two periodic sequences, then what is the result? Result is also a periodic sequence with period which is LCM of these two periods, right? So you have actually multiplication and convolution. However, for discussion, for simplicity of discussion in this, let us take x1 of n and x2 of n. Both have a period of capital N. Okay. So let x1 of n and x2 of n have period of capital N. Okay, then let us start this discussion. And if we multiply in time domain, okay, this is x2 of n. If you multiply in time domain, in DFS, it will be convolution. This convolution is not like, unlike the normal convolution, it is referred to as periodic convolution. Okay, so that means, see, as you know, if time domain signal has a length of n, okay, n samples, what do you expect after DFS? The length of, say, n samples and repeats with it. In fact, it's not the length of sequence, it is the period of the sequence, right? So period, periodic with period n. Okay, then DFS also is periodic with period n. Okay, so how does it happen? This happens because this is not a normal convolution and this is a periodic convolution. We'll see why does it come and what does it mean, right? Similarly, in frequency domain, if you have a multiplication of two discrete Fourier series, okay, each is periodic with period n, then in time domain, how does it reflect? Is periodic convolution in time domain. Okay, so let us take the second expression. Let this be first and this be second. Okay, let me give some idea on how to prove second, and I suggest you to try to understand and discuss on the first relationship. So let us take this. See, what do we mean by periodic convolution? I will define it first. X1 of n, x2 of n. Okay, so if we take any two sequences, what is convolution? X1 of k, x2 of n minus k. Okay, this is the convolution, right? Let this be x3 for simplicity, and this is how we define. And k varies from minus infinity to infinity. That's what is usually what we define. However, this signal is periodic here, so you can't define from minus infinity to infinity. So what we do is we define over a period, right? When we define this over a period, this will take all the samples, say this will take all the samples of a period. However, here if you see, n minus k will have a shift from 0, okay, and start shifting from 0 and takes different values. So what did we discuss in the previous discussions is that if there is a shift in a time domain, okay, how does it reflect for a periodic signal? Is that it reflects as a circular shift, okay, rather than a linear shift. Okay, for a periodic signal, it's like going from minus infinity to infinity. If you start from here, it is just up to here. Okay, so if you start from here, okay, it is up to here. Okay, if you start from here, it is up to here. Okay, if you start from here, it is up to here, and so on. Okay, if you start from here, then it is up to here, something like that. So it keeps changing the range. So it is like moving in a circular, on a circle with same set of samples occurring again and again. Okay, say this, if these samples spans a period, same set of samples occur again and again, you may start anywhere. And from there, the sequence will come. And it's referred to as circular shift. Okay, and that's what is being done for a periodic signals when we shift them. So when we consider here in computation of convolution, we consider with not with linear shift but with circular shift. Okay, to enable us to write them as with modulo n operation, to enable us to compute the necessary convolutions only with the samples which are distinct from each other. Right? If you take 9 samples in a period, only there are 9 possible distinct samples. And when you repeat, same samples will come again and again. Right? And hence, this is how the circular periodic convolution is defined. Now, given this, so let us see, take the Fourier transform to see this relationship. Okay, so let us apply now x3 tilde of n. Okay, based on the notation x3 tilde of k, based on the notation we have. Okay, that is summation. Here, let this be to have a easier notation. Let this be okay. Instead of k, let us take any other expression here. So p. Okay. Okay, so that actually we will we can stick to k here. N equal to 0 to n minus 1. Okay, here we can stick to k. 0 to n minus 1. x3 of n tilde of n e power minus j 2 pi by n nk. Okay, and when we expand, n equal to 0 to n minus 1 and p equal to 0 to n minus 1, write x1 tilde of p, okay, and x2 tilde of n minus p, but with circular shift. Okay, e power minus j 2 pi n nk. Right? Okay, so let us take the p terms outside. Okay, so to simplify this is p is equal to 0 to n minus 1. What we are looking at is x3 of k, that is dfs of x3 tilde of n. Okay, right, x1 tilde of p into, sorry, n equal to 0 to n minus 1, fine, and x2 tilde of n minus p modulo n e power minus j 2 pi by n nk. Now, please see what should we write for this? What should we write for this? This is nothing but what? So this is x2 n minus p, whichever we had here. Okay, so when we said shifting, The shifting, as I said, the shifting, though we can write here, strictly speaking, it is a, if we consider only one period to write n minus n naught, this is with modulo n operation. Okay. So, and hence you can write this as x tilde of, right, k into e power n minus n naught, right, e power minus j 2 pi by n into p into k, right? So p into k, because as we have written, n minus n naught is e power minus j 2 by n naught into k. That's what we have written here. Now let us substitute this here. Okay, so x2 of tilde of k, right? So let us substitute this here. Let me put it here. X3 tilde of n, that is, let me write here dfs of x1 of n, okay, convolution with circular convolution or periodic convolution with x2 of n. Okay, periodic convolution means whatever we have written here. Okay, so right, with circular shifts. Okay, so that means the sample, if you have the first sequence in period 0 to 9, okay, 0 to 9, second period is from say here, say 4 to 4 to 13, okay, then we element wise multiply this sequence, okay, this sequence and this sequence to get the x1 tilde of, so element wise multiply these two sequences to get us the x3, okay, tilde of n, right, the third sequence. Hope this depiction is clear. Okay, let me sketch a thin line if right. So what we are doing is this operation. Okay, hope this is clear. This is the circular convolution. Okay, you can see actually this is also referred to as circular convolution or periodic convolution. Okay, since there is a periodicity involved here, we call it as periodic convolution. Especially in case of discrete Fourier transform, when I define and so on, we'll call it as circular convolution there, because we keep circularly shifting the samples. When we see only one period, it is like a circularly shifting the samples. So that means these samples now, whichever we see here, these samples, okay, come and these samples, whichever we see here, will come and sit this side, okay, to make the inner product in this region, okay, in this region and in this region. Okay, that we'll discuss in the subsequent classes. Okay, let's continue and complete this discussion. So this is equal to whatever we had, summation p equal to 0 to n minus 1 x1 tilde of p into what do we have, x2 tilde of k, because already we could write this as discrete Fourier series quotients, into e power minus j 2 pi by n into p into k, right? And this is equal to x2 tilde of k into x1 tilde of. Please note that if you take it out, this is exactly what you see here. So for simplicity, if we write, okay, so let us anyway write. Okay, so if you leave this, the remaining things, if you write p equal to 0 to n minus 1 x1 tilde of p into e power minus j 2 pi by n into p into k. Okay, this is nothing but what? x1 tilde of k, right? And hence you can see that, okay, you can see that x1 tilde, okay, all are tilde with tilde, n periodic circular convolution with x2 tilde of n, okay, give rise with dfs as x1 tilde of k x2 tilde of k. Okay, right. So the convolution becomes multiplication and multiplication becomes convolution, with only change that it is now periodic convolution, because we wish to restrict the number of samples to be 9 or over only one period. Okay, these samples will come and sit here to make the sequence equal length, and then we multiply, right? And then we keep correlating or multiplying here, right? Now similarly you can prove the other relationship. Thank you. So we will discuss in the next class how to relate this discrete Fourier series quotients to discrete time Fourier transform of a aperiodic signal.